Chetan sir, we are live now. You can start.
All right.
Okay.
So,
Good afternoon to all present here on a virtual desk. Today's resource person, Mr. Khalid Khan, our principal, Dr. Sanjay Bokade, principal, Dr. Sanjay Deshmukh, head of the department, Dr. Rajesh Kale, teaching, non-teaching staff, and all the participants. I, Professor Chetan Rane, on behalf of MCT's Rajiv Gandhi Institute of Technology and Department of Mechanical Engineering, welcomes you all for the fifth day, second session of ASCT AQI sponsored online 1 week short-term training program on recent trends in energy management and audit. Today we have our resource person for this STTP, Mr. Khalid Khan, with us. He will speak on thermal system analysis. I take opportunity to introduce our today's resource person, Mr. Khalid Khan. Now, Mr. Khalid Khan is currently working in IECS as a senior energy auditor associated with the activities of energy conservation and conducting site assessments of client processes on energy and cleaner audit aspects in various industrial sectors nationally, focused on handling and executing several green projects from multilateral organizations on accelerating and promoting environmental sustainability aspects in industry and financial sectors. Also active in organizing and presenting workshops in industrial sectors on topics of energy efficiency, clean tech, financial, climate change, and clean technology. I welcome you, sir, and thank you for joining with us today. I request you to enlighten us with your wisdom words. Thank you, sir. You can start, sir.
right, sir. Thank you very much, and thank you for giving us this opportunity. And let's start with this presentation on thermal systems. I hope all are able to hear me, and my voice is clear. And if you have any problem, then maybe you can tell me so that I can improve. Right.
Yes, sir.
Okay. So basically in this presentation, I would like to share you in terms of understanding the practical aspects of a thermal system. We have lot of thermal systems, whether it's a boiler, it's kind of a thermal system because we are using a thermal energy in it. There are furnaces, it's also a thermal system. We have hot water generators. So there are various kinds of thermal systems we come across in an industry, and sometimes it is used in institutes and buildings, hospitals, kind of. So just to understand how to analyze those thermal systems in terms of their energy performance, and what kind of data collection to be done before analyzing those systems, and what instrumentation should be used. So that kind of approach will be there in this presentation. The presentation is made solely on my own data collection, my own experience in the field, and I have collected these points just to understand the basic, the fundamental aspects of understanding the analysis of the systems. So as I told you, we have a lot of thermal systems in industries, furnaces, boilers, hot water generators, hot air generators, thermic fluid systems, ovens. So based on the requirement of a process, whether we are working for a metal industry, for aluminum, for metal melting, or reheating a metal for some kind of shape change, boilers for steam generation, hot water generations for process requirement, and similarly ovens are used, thermic fluid systems are used in the processes. So the approach we should have, like for all these thermal systems, should be that whatever system should be is there in an industry or in a plant, there are few aspects that are common in all these thermal systems. That is, the first is the operating temperature. Whether we are having a furnace or a boiler, or there is always a certain specific temperature requirement. Suppose if we are melting aluminium, then there is a specific requirement that a metal will be melted at 750, or it is required 740 degrees Celsius, that the minimum temperature has to be maintained, below which it will impact the pouring and that efficient casting will not be achieved. And if the metal is overheated, then there will be losses in the metal again, we will lose the metal. So in both the cases, there will be a loss, financial losses as well as the production losses. And then the other aspect in any system will be a air to fuel ratio, because whenever we are having a thermal system, we will be using certain kind of fuel, whether it is a solid, liquid or gaseous fuel. So each fuel has their specific requirement of air to fuel ratio. So maintaining a correct air to fuel ratio will help us in achieving the better efficiency of the equipment, lower cycle time. The third point is the waste heat recovery. In each system, always we have to see the scope of waste heat recovery wherever possible, because the waste heat recovery will not only save our energy cost, but will also help in reducing the cycle time and save also the environmental benefits. Surface insulation is another point which is a very important. So every hot surface should be insulated. Also, insulation should be regularly monitored for better efficiency. Another is energy efficient air blower, because for any system we will simultaneously require certain kind of blower that will give us the air for the combustion of a fuel. So this blower, which is being used for supply of combustion air, this blower should itself be efficient to supply the correct amount of air for the complete combustion of the fuel. So all these are the major aspects that should be incorporated into any thermal system to make a system efficient. So these are the broadly points. Now, understanding the of these on the performance of our thermal system, like coming to the first point, operating temperature. See, operating temperature close to our operational requirement as we can, because as I told in previously that deviating from the required temperature will impact the efficiency of our thermal system. So higher the temperature, the lower the efficiency and higher the metal or scale losses. Similarly, as I said, that if the temperature requirement of our process is suppose 750, and we are making, or we are going to a higher temperature than 750, suppose we go to 760 or 770, then the efficiency of the system will decrease. As a system, efficiency of our thermal system will decrease. And if it is a metal, then there will be higher scale loss. Suppose if we are using like if we are doing a forging, then definitely at higher temperature the scale losses will increase, the metal losses. Or if we are melting, then there will be like, so it will be again a material loss. So there is a small thumb rule: for every 12-degree rise in temperature, efficiency drops by 1% for the furnace. Again, similar example I will give. If there is a temperature of suppose 750 degree and we are going for a higher temperature, suppose 762, just 12-degree high. So overall efficiency of the furnace will reduce by 1%. So speaking in this presentation, it might sound for some people or like the 1% is a very small number, but if you take this 1% in terms of like furnace into financials, then sometimes the furnace this 1% might lead to like a financial losses in lakh of rupees, and if the furnaces are very big, even the 1% can give a losses of crores of rupees annually. So even a 0.5%, 1% efficiency plays a very important role in any thermal system. So that's why the operating temperature should be very close to the operational requirement. Another, if we take an example of like steam, for in steam, every 4.5 kg per centimeter drop in pressure will increase in efficiency by 1%. In boil, if we are having a boiler and we are generating suppose a steam of 5 kg per centimeter, or you can say 15 kg per centimeter square, and if there is a requirement of just less than that and we are generating at higher pressure, it most of the time happens, people take a safety margin of sometimes 10 kg, 15 kg, 20 kg. So depending upon what happens, the plant may use a higher requirement of the like a higher generation of the steam, and there is a requirement at low pressure. So in steam also there is a thumb rule that if 5 kg per centimeter square is dropped in pressure, then it will increase the efficiency by 1%. The next is a parameter is air to fuel ratio. This air to fuel ratio is a very critical parameter. Again, it should be very optimum. Let us understand any combustion of any fuel. We require a certain quantity of air, that is the exact air quantity. So that exact air quantity comprises of theoretical air requirement that can be estimated from combustion theory. If the people are from maybe from power plant or from mechanical engineer, they must be knowing, or a chemical engineering, they must be know that for every carbon present in fuel, it is combined with oxygen and forms carbon dioxide, right? So the amount of carbon present in a fuel will combine and give CO2. So that will be equal to the theoretical requirement. Now, apart from the theoretical requirement of the air, there is a requirement known as excess air required, right? So theoretical air will combine with carbon particles and excess air is required. So what is the requirement for excess air? So excess air is basically required for the mixing of the fuel with air. Suppose there is a certain amount of theoretical requirement, and if we will give only that amount of air, then it will happen that the that fuel and our air will not get mixed properly. Means all the carbon in the fuel will not come in contact with the air, and there can be a partial combustion, and in spite of converting from carbon to CO2, it will lead to carbon monoxide. So it will not form CO2, it will form CO, carbon monoxide. So for proper mixing of air and fuel, we need to provide the excess amount of air for the proper mixing. And the amount of excess air depends on the mix of our fuel. Mixing capability fuel. We have three kinds of fuel: solid, liquid, and gas fuels. The mixing capability of solid fuel is lowest. The mixing capability of liquid fuel is higher than the solid, and the gaseous fuel has the highest capability of mixing. So simultaneously, when we will require the excess air, so in that case, we will require high excess air for solid fuel, then for the liquid fuel, and less for gaseous fuel, because gas can easily mix with the air. So lesser the mixing capability, more the quantity of excess air. In our system, if the solid fuel, if we say that has a lesser mixing capability, then amount of excess air required will be high. So from this point, we can understand, if we have a boiler of, suppose one is there are three boilers. One boiler is operating on solid fuel. The second boiler is operating on a liquid fuel, and a third boiler is operating on a gaseous fuel. So the boiler which is operating on the solid fuel will have the larger size of combustion air blower, which is giving the air to the for the mixing or for the combustion. Then the size of the liquid boiler blower will be less than the solid, and the size of the blower for the gaseous boiler will be least. Right. So this is the basic principle which I was discussing about. The fuel ingredients generally has carbon, which combines with oxygen gives CO2. We have hydrogen, which give H2O, and if there is sulfur present in the fuel, which generally sometimes the fuel has like you can say furnace oil generally has sulfur in it, then sulfur will combine with oxygen and will form SO2. So depending upon the ingredients in the fuel, we need to supply the uh, oxygen through our blower. So the excess air should be supplied into the system. That's right, what I told. But at what level, up to what level this excess air is sufficient? Because if we will supply us excess air, suppose just 10%, and a system is having efficiency of suppose 85%, then if the excess air is increased, then what will happen? Efficiency again will decrease. Further, if it is increased, to identify how much quantity of excess air is sufficient for us or for our thermal system. And along with that, the stack temperature should remain constant. So looking at this effect of air quantity on efficiency, this graph will give you like a picture. See, excess amount of air which we are delivering into we are supplying to our system should not be less and should not be high. If you see on this graph, we have the x-axis on which we are showing the amount of air quantity which is supplied to the system for the combustion of the fuel. If you see on the y-axis, it is showing the efficiency percentage, means how the efficiency will increase or decrease, right? if you see this point, so this point you can say that this at this point the system is having the maximum efficiency, right? Now if we go to this side, means this is the optimum quantity of air that will give us the maximum efficiency, right? Now if we go to right side, and if we increase the air, if we are increasing the air quantity, what is happening? We can see that the value of efficiency or the system efficiency is decreasing. Understand? Now you can see, if you see from the left side again, if we are reducing the quantity of air from that is required from the optimum value, from this side again the efficiency of the system is decreasing. Here the efficiency will decrease again. If we have reduced, again the efficiency will decrease. So from this we can identify that this point is the optimum point at which the efficiency of the system will be high, and going to the left or right to this point will decrease the system efficiency. But again, the important point which needs to be understand here, that the graph showing in blue line, the efficiency of the system decreases very rapidly in case if we are supplying less air compared to what is optimum quantity, compared to when we are supplying a high air, excess air than this point. So this will decrease the efficiency more quickly than this side. So the best is we should maintain the oxygen or the air level, combustion air level at this point. If not, then at least at this level, from this side, not the blue side, because this will give the major negative impact to the efficiency of the system. Now now in your mind you must be thinking that from understanding the graph, looking at the graph, yes we are understanding, but from the practical aspect, when we are in the field, how we can identify that in what area, whether we are in the less air side, blue side, or we are in the excess air side, that is red side. So which is at which side our system is operating. So for that there are different like ways which can be like that at which side we are working. This is one of photograph which we took during our audit. Basically this is a furnace using natural gas, and there are a lot of that were running and showing a blue flame. So from this basically in this furnace, this sanitary is like baked. So we took this photograph when this furnace was running in this condition. Then we just changed the setting of one of the burner. If you can see a left side, that one of the burner, the flame is almost like a orange or reddish flame, right? So and identify, this can be one of the way we can identify whether the system is working correct or not. If the burner is working fine, then it will give a blue flame. And if the burner is there is some problem or some issues in the burner, then the flame color will give us like a visual inspection can also give us that there's some issues in the combustion of the in the system, and the efficiency of the combustion blower is not okay. So this can be one way, like a daily aspect. If at your home or having cook stoves in kitchen, so when we like lit this cook stove at our home, this shows a blue stove, you will see that the flame color will change. So that is the another that you can see an indication at your home that if the burner is okay or not. So this can be one way, but like a visual inspection. And another way can be like measurements with the tools that are the like to give the proper values from which we can identify whether the system is okay or not. So from practical aspect, from the industrial aspect, to identify working or not, we do a measurement, and that is known as like just coming to the this with this meter, that is a portable combustion analyzer. This is one of the instrument that identifying the combustion efficiency of the system. So with this system, if you see, you have a meter and then there is a probe. This is the probe. So with this probe is inserted into the chimney, from which this combustion gas system. So when we insert this probe into the chimney and we operate the meter, this meter gives us the value of carbon dioxide, carbon monoxide, uh, oxygen, and the temperature of the gas we get from the system. And from these values, we can identify at which range our system is operating. Systems, we have different ranges that are okay, as you can coming to this slide. We have a pulverized coal system or like a stoker pipe. So the oxygen percentage, if the meter is showing that the oxygen percentage is 4 to 5% or 4 to 6%, depending on the best oxygen level. So if it is coming high in your system, in your meter, then you can say that the oxygen percentage is high. So we are giving excess oxygen through our combustion blower. So we need to optimize the flow that we are supplying for the combustion. In case of liquid fuels, you can see from the oil, the oxygen percentage generally is should be in the range of 1 to 3%. So if we are analyzing any system which is operating on the gaseous liquid fuel, whether it is diesel or whether we are having FO, so the level of oxygen which we will measure from our meter should be in this range, 1 to 3%. And similarly for the natural gas, it should be in the 1 to 2%. Some meters also some meters define like gives the values in terms of excess air and excess air, and some meters gives directly the oxygen percentage. So if you give you are getting a percent like oxygen and you want to calculate the excess air, that can be calculated. There is a simple formula. And if you need to directly see the oxygen percentage, which is a clear indication of how the system is operating, so you can work on that. So depending upon the industries work on the different like parameters, but for all, the point is saying that they have to maintain the optimum oxygen percentage in their systems. Yes, again, this slide shows the efficiency levels. These can vary from, or you can say, the original equipment manufacturer. Suppose there are a lot of companies which are manufacturing the boilers. Every boiler supplier gives the values of the at what best efficiency their system is designed. So when we are analyzing our system, doing combustion analysis through our gas analyzer, so we can come to know at what our efficiency is designed for and at what efficiencies we are operating. So there are formulas available that can give efficiencies. So I'm not going into that details that can, if you need those formulas for calculating the efficiencies, I will provide you. So there is no issue in that. Even the BEE Site Bureau of Energy Efficiency, and that has all the details, that formula and calculation in that. If anyone wants to know the calculations, how efficiency is to be calculated, you can go through it, and maybe in all the books we have the formula calculation for the efficiencies. Another important point is the air infiltration. What do we understand by air saying an air infiltration? Let me see if we have some diagram. So I was having, I don't know. Okay. So basically air infiltration is, see, in any system we have, if we talk of a boiler system, so in a boiler we have a generating a steam. After combustion, the boiler, this hot air, we what we do is we install a different equipments with us for the heat recovery. We have air preheater, then in line we have like economizer, and then dust collectors are there, and then after that we have ID fan, and from that ID fan the air, this combustion air goes to the chimney. So there are 4 5 equipments from boiler to the chimney, through which this air, this combustion air goes after releasing the heat. So if at the boiler, at the exit of the boiler and before the chimney, if there are some holes in the system, so because this whole system will have the negative pressure, as FD fan is like sucking the air from the boiler, ID fan basically. So what will happen in the system, that from the hole the air will get infiltrate into the line, and this infiltration will cause various negative impacts on our system, like when air infiltration will occur, then the amount of air, the quantity of air that will be handled by the idle fan will increase. And when this volume will increase, then the power consumption of the fan will increase. So this you can understand if in a like a power plants or in a big industries where there's a like a 1000 kilowatt ID fan, or in fact in boiler it is in megawatts. They have a 1 megawatt fan or 2 megawatt fan. So in that case, if suppose there is a small volume of 1% or 2% is increased through infiltration, then the fan power consumption will increase, and it will like in, if you convert this into cost, then lakhs of rupees will be like wasted in just because some holes are there in the system, and we are having the higher quantity due to infiltration. Another negative impact that we can see is because of the metal corrosion. In case of coal, or in case of pet coke, or in case of other solid fuels or liquid fuels, if some sulfur is present, then what will happen? The SO2, the temperature will decrease of this SO2 formation because of the sulfur, and this SO2 will react with the moisture present in the atmosphere and lead to the sulfuric acid formation, H2SO4. and this H2SO4 will stick to our structure, chimney, and other equipments, and this will corrode and corrode the system, and it will impact the operation and the production. Now, that infiltration will have the impact in lowering the fuel combustion air temperature, and that has a different negative impact. But in case if we have a high temperature, we are giving a high temperature in the chimney, which we can recover, then it will also give a negative impact. Like, higher temperature means we are not recovering heat that can be recovered. Then excess fuel firing, we have to provide excess fuel, again a cost. Foul tubes, because higher temperature the scaling will be high inside the tubes of the boiler. If it is a boiler, then it will impact the efficiency of the boiler, and ultimately the tubes will be choked. So reasons for fouling: generally combustion particles deposit, and sometimes if the water quantity we are for which from which we are generating the steam is not treated properly, then this will also lead to the reduction in the operating efficiency and of the boiler. So in this also there is a every 22-degree drop will give the 1% efficiency increase. This you can understand by example. Suppose if the combustion air which is going through the chimney of our boiler, and it is giving the temperature of this air is suppose 250 degrees Celsius, and if there is no sulfur present in this system, then it means this 250-degree combustion gas which is going to the chimney, we can recover this heat through by installing some waste heat recovery for heating water or something else or air, and we can reduce the temperature. Maybe from 150 degrees C, the temperature of this combustion gas can be reduced to maybe 150 or 130, and this recovery of heat can be used in some other processes. If you have seen if we and for that we need to see key utilization of this heat where we can utilize in the system. So ultimately, utilizing the waste heat from the combustion gas will reduce the fuel combustion in our process. So it's always better to reduce the exhaust temperature as low as possible, depending upon the sulfur quantity. Then the temperature of the fuel, like a gas, should not be reduced below 150 degrees C. So this shows one of the that how much sulfur is can be acceptable, how much temperature should be maintained. So if you see on the x-axis there is a percentage sulfur in the fuel, on y-axis if you see there is a dew point of flue gases. So suppose there is a much, and if the flue gas dew point is 140 degrees C, then we should maintain this temperature of the flue gas above this minimum metal temperature to avoid the corrosion. So every metal has this temperature limit. So always the flue gas temperature should be above this point. Another point is the waste heat recovery. Another point is the waste heat recovery, as we discussed some points earlier in the slides. So when do we recover the heat? Pressure of the gas which is going out of the boiler or furnace is high, then we can recover the waste heat. And simultaneously, the system, that thermal system, a boiler or a furnace, should be continuous in operation. If it is not continuous, then the recovery will not be like in terms will be not efficient, and it will not give the payback, or the return on investment will not come. Advantage is it will reduce the fuel cost and simultaneously the heating time, cycle time. Now another important point is the surface insulation. Insulation should be adequate. It should not be high. It should not be less. So there should be always optimum quantity of insulation that should, whether we are having a cold like minus or lower temperature as compared to ambient, or if we are having a higher temperature in a steam or a furnace. So whatever systems we are having, it should be properly insulated. And for the insulation, there are some thumb rules which I suppose temperature of any system is set will be 1500 kilocalorie per meter square per hour of energy loss. And if it is insulated, and now the surface temperature after insulation is coming out 70 degrees C, then it has been reduced, the energy loss is reduced to just 1/3. We all know that how the insulation losses plays a role. The fourth power to the power 4 in temperature uh,
Hello, sir. Is there any problem?
Hello,
Hello, sir.
sir.
Hello, Khalid, sir. Chetan, sir, am I audible to you?
Yes, you're audible. I think sir has
sir, I got muted
sorry,
somehow.
muted.
So
Muted.
now is it, are you able to hear me?
Yes, sir. Yes, sir.
Yes, sir. So just we'll go through some practical case studies.
Okay, sir.
There were 3 furnaces in a plant. We did the energy audit. So just need to ask how much time we have.
Sir, we still have 20 minutes, sir. 20,
Okay,
20
fine,
minutes, sir.
fine. So I'll
But,
cover.
sir, your PPT is not visible.
Okay.
Yes.
Till now or just?
Just now, sir. Just now.
Just now.
Yes. Sir, it is visible now, sir.
So I hope all the slides which we have discussed last were visible.
Yes, sir. Yes, sir.
So think that we did the audit of a plant in which there were 3 furnaces. So what we do, we did the analysis on all these points which we discussed just now. We saw if the operating temperature. So there was no monitoring of the operating temperature. There was just like a idea that the temperature has achieved and they start processing. Then for air to fuel ratio, they were having no meters on the fuels, how much fuel is being consumed in different furnaces, because there were three furnaces. In each furnace, how much fuel they were consuming, there was no metering, no proper control of air to fuel ratio, because there were no measurement on the combustion gases. Again, there was some issues with the boilers, in which they were controlling or the combustion air with the dampers, or we can say a valve controlling manually. Poor burner efficiency, as the flames physically inspected were showing the orange flame. There was no waste heat recovery, as the waste heat recovery was not working properly, and no temperature gain was achieved after installing several openings in the into radiation, high radiation losses. There was a high, all the hot air was coming at a high pressure from the furnace. Surface insulation was poor. The recuperator which was installed for waste heat recovery, it was not insulated. So just to see from the a photograph, this was a furnace. There was a opening, the flames were coming out, and the thing that should be there, that the flame should have been inside, and it should not be that it should come outside. So all the flame length which is coming out, it is just a loss for our fuel. There were large openings. If you see, there are this is a right side. If you see, this is a thermal image from the. There's an instrument which is used to do the thermal imaging. We took the thermal images to analyze the temperatures. Again, there are a lot of openings. This was installed and it was not insulated, and also you can see that it was not for the proper heat, and no insulation was provided on the surface. This was the line of the for which the air was supplied, and the line was not insulated. Again, no insulation. You can see from the red, and this scheme of the colors shows that at which range our point is, at which range. This is again there was no proper insulation, and heat was being so hot at very high temperature. You can see from the scheme of the color.
Sorry to disturb you, sir, but I think your voice
is
breaking.
These kind of losses were occurring. Data. Yes.
Can you hear me? Sir, your voice.
Okay.
Sir, your voice is breaking.
So.
Hello, sir.
My voice is breaking.
Yes, sir.
Okay, the connectivity, if there is an issue. Let me see the connectivity. Is it fine?
Yes, sir. Connectivity is fine, but your voice is breaking in between, sir.
Okay, let's start if you have the issue.
Okay, sir.
Okay,
sir.
So in this system, after doing all the physical analysis of all these parameters and the systems, we did the some calculations for the efficiencies. So what we did, we calculated the specific fuel consumption of the furnace. So first we have calculated what is the typical rate of heat. That is means 1000 kg heat of the aluminium. It was basically aluminium that was being melted into the system was 0.22 kilocalorie per kg degree Celsius. And they were raising the temperature of that furnace from 30 degrees C to 730. So it means there was a delta T or temperature difference of 700 degrees Celsius. So with the formula NCP delta T, we have calculated how much will be the theoretical heat required that will go into the metal itself for the thing. Right. Apart from that, there will be an amount of heat that lost because of the inefficiency of the furnace itself that are bound to happen. But what then we tried that if the efficiency of the furnace of these type is in the range of 25 to 30%, then considering the 25% efficiency, then amount of heat that has to be supplied into the system will be like 6,16,000 kilocalorie, right? And the GCV of the fuel was 10,000 kilocalorie per kg. It means we need to require 61 ton of fuel per ton of melting the material. Now, if the efficiency, suppose we assume at 35%, then the fuel consumption will be uh, like 4,40,000, because if we are taking a higher efficiency again with the same GCV, so the fuel consumption will be 44 kg per ton. Now, this was the like a theoretical calculation we did. Now, we did the actual calculation of what the furnace was operating. So we took the production data. This was the production data. There they have melted 782 ton. This was the fuel consumption they have uh, given. Actual what fuel consumption they did, and with that we calculated, and it came out 73.88 kg per ton of fuel melted. So approximate efficiency was just 21%. And for other furnace, Skellner furnace, one was a tower furnace, one was a Skellner furnace. So you can analyze that there were a lot of issues which we discussed earlier, that they have to take the actions on all those issues. They have to install the recuperator, insulation, they have to recover the waste heat, they have to manage the openings, they have to manage all these things. If they will work on those, then they can improve the efficiency of their furnace. And from that it was calculated, if they increase the efficiency just by 15%, then it will give the saving potential of around 20 lakhs with just an investment of 10 lakhs. So this way the furnaces can be analyzed. This can be one way people can analyze on different and ways depending upon their understanding of the system. So this was an example of a furnace. Now coming to one of the example of the hot water generator. So for hot water generator, again the system was generating a hot water, and we did the flue gas analysis with our meter, as we have shown in one of the slides. Oxygen percentage, what is the carbon monoxide, all those values we measured. This was the measured values: oxygen percentage, carbon monoxide, parts per million, stack temperature, CO2, and what was the recommended. If you see that the oxygen percentage was recommended for that system of 3 to 4%, but it was actually operating at 13%. Similarly, the carbon monoxide should be less than 50% ppm, and it was operating 4,000. Stack temperature should be less than 150 degree, and it was operating 210. CO2 should be in the range of 13 to 15%. It means 3 point, and it was operating at 3.2. It means there are disturbances in the system, and it needs to be rectified. If you can see, in case in any system, just for the understanding, if the oxygen percentage is high compared to what is being recommended, see this is high, then this recommended, then the value of CO2 will decrease, because it means the proper combustion is not taking place, and because of improper combustion, CO is not combining with CO2 and not forming CO2, and it is just partial combustion will take, and CO will combine with O and will form CO, carbon monoxide. So incomplete combustion will increase. So that is what happening in this system. So from these values, you can understand that what is happening in the system. These will give a clear-cut picture what was happening. So then the efficiency was calculated. This is the indirect efficiency calculation. There's a lot of formulas given in the book, as I told, in the BW book. we have the ready-made Excel because we work regularly on the system. So we have four values, these four values, and we get the value of overall efficiency of the system. So we got the overall efficiency, and then we suggested the measures, what the action plan should be, that they need to proper monitor with the flow gas analyzer. They need to have the drive which should control the air, and with that they should see if they should reduce the amount of air that is being supplied, and make an optimum supply for the efficiency improvement. So if the running efficiency is say it was 70%, and if even the 5% increase is done, then this was the financial benefit. And for that they just need to have one like a VFD on their floor for the speed variations, and they need to have a meter to analyze the values. That is a flue gas analyzer. Another, so this was the example for the gaseous fuel. Now again, coming to the hot water generator with a solid fuel, we did the same analysis, and we did the analysis based on like the operating cost. So this hot water generator was working on a HSD, and we did the calculation of different fuels. What is the costing that is they will get to generate the same amount, to get the same amount of heat energy by different fuels, LPG, diesel, and biomass. So what is their GCV? What was their rate? Because now the rates are changed. This PPT is a bit old. And what is the maximum efficiency that we can get in the system? And with respect to that, what will be the heating cost? Rupees per million kilocalories. So if you see, this biomass is was coming out a very low cost as compared to LPG and diesel. In fact, this is now a big higher than what is right now. So we can like take a decision which fuel is more economical to us, and based on that we can change the decision if we need to change the existing fuel system, or we need to make, or by some modification we can save the cost. So when we suggested the improvement and suggested for the biomass fuel, then this was the saving potential identified, in which we suggested to replace that system with a new system, and this was the annual saving. Means in all the projects, all the case studies we have discussed, the saving is recurring. Annual saving means every year they will get the saving, and investment is done only once. So these were some of the systems and some of the practical case studies of the thermal system that we can analyze in any system. So if you have any queries, you can ask me, or from the organizers. If you have any queries, you can connect me. Okay, so thank you.
Okay, sir.
Right.
Thank you so much, sir. Indeed, it was a session filled with knowledge. With your permission, I would like to take up the question and answer session.
Yes, please.
Over to you, Ratna madam. Ratna madam.
Hello? Hello, sir?
Yes.
Hello, sir, am I audible?
Yes.
Yes, you're audible.
Sir, there are few questions I would like to ask you. May I have your permission, sir?
Yes, please.
Okay, thank you, sir. Sir, the very first question is, why air quality index of Delhi and other cities are deteriorating during winter season, and why air quality index parameter values are different for different cities?
Basically, you must have heard in the news as well that it is deteriorating because of the stubble burning in the neighbor states of Delhi and this UP, Haryana, and Punjab. So because of the stubble burning, it was seen that there is change in the air quality index continuously after the this season of harvesting. So this is the major reason. And uh, in fact, this year, if you see that, because some lot of efforts being taken by the government, lot of a media attention was given, so because of that, this year the situation is better compared to the last year. So somehow you can say that this was a correct identification of the reason of air index, quality index. And regarding the different air quality index for different cities, what that I think, mm, for me, I don't have the complete information that whether the different qualities have different parameters of air quality index. So you need to go through like a website or something for that. I don't have the values of that.
Okay,
That
thank you, sir.
right.
There is second question, sir. Which softwares can be used to design and simulate thermal systems?
See, for thermal systems, software I haven't used, because we, as an energy auditor, we have our instruments and we do a practical, like a measurement of the existing system. So we don't design the system, we just analyze the system, existing system. But there, yes, there are software in the markets. People do CFD analysis, computational fluid dynamics analysis, uh, for the a heat transfer and all. And there are a lot of other softwares people are using for the designing of heat exchangers, people designing for the boilers and all. So and they, from manufacturer you can contact, or I can support you by getting in touch with manufacturer. We practically come across with the existing systems which are already installed in plant or a factory. So we only do the analysis, and based on our analysis of the existing parameters, we give the recommendations.
Okay, thank you so much, sir.
Right.
Thank you so much for your guidance. Now I conclude our question answer session. Over to you, Chetan, sir.
Okay, I request Professor Mukund also to give vote of thanks.
Hello. It is my privilege to propose a vote of
Yes, sir,
thanks
you are audible.
on this occasion. I, Professor Mukund Valse, on behalf of MCT's Rajiv Gandhi Institute of Technology, Department of Mechanical Engineering, and on behalf of Organizing Committee of AICT AQIS, sponsored online short-term training program Phase 2 on recent trends in energy management and audit, and my own behalf, extend a very hearty vote of thanks to Mr. Khalid Khan, sir, for accepting our invitation as a resource person and sparing his valuable time with us. He has given a good insights on the topic of analysis of thermal system. He has covered the topics such as energy audit approach in thermal system, parameters affecting the performance, basic principle of combustion, instruments, and practical case study. Thank you so much for your great session. Tomorrow on 20th November 2020, morning at 10 a.m., we have day 6, session 11 by Mr. Panduranga Jalkote sir on the topic PAT mechanism of BEE for industries and role of energy manager and auditor. I request all the participants to join the session. Thank you. Thank you very much, sir.